RK method. Okay, we'll try to uh, solve this spring mass damper system using in a MATLAB. Hmm. Actually, when I say in a spring mass damper system, in this case, what it happens when you're going to have a spring mass damper system. Okay. Okay. So we have a mass here, then there is a spring, and then there is a damper. Typical equation for this is mx double dot plus cx dot plus kx. This was the equation, okay, and which is equal to 0. This is for free vibrations. And here it is in a x is nothing but in a degree of freedom for this equation, because we are going to solve such equation and numerous equation in most of the places in mechanical engineering. So that's what I took this as an equation, one of the equation. So in RK method, what we done it, RK method is to solve ordinary differential equations. Problems. First order ODE, ordinary differential equation, we can solve it. So what is the way it is solved? Actually, the thing is like that. This is what on a time, and this is what on x. So you can take in a simple equation that is in this case we have an equation that is x dot is equal to some function of x. So this equation has a solution in this pattern. Basically, this may be the solution. We have an initial condition at time t equal to 0. You know that x0 is the initial condition. What you will do, you will determine this is my starting point. I'm going to determine the next point, maybe at time t equal to 1 or something, and having a single step solution. So this is nothing but my straight line. So here this equation is equal to y is equal to somewhere mx plus c I can do it, and I can get the solution at this point. Okay, by taking an only one single k, I can say this young as a one slope of this. C is nothing but my intercept. That intercept I can extend it. Here I can get a C value or something. So this is what in a Runge Kutta method, single step solution, and that is basically it is written like this. Y, maybe I can say it is an x1 is equal to a, or I can give an instead of k, I can write an yam into my initial condition x0 plus c. So what are this yam is nothing but in a slope. In RK method, what they have done it, if I look into the typical graph of this, what it happens, so this is my first point, is d0 and x0, okay? And this somewhere I want to determine a t1. So this is nothing but in a domain, or within that I want to determine that this is a step size, I can say. Is it? When we are solving, we may be taking not on a single slope, we may be taking in a multiple slope at different location, maybe here, maybe here. If I'm taking two slopes, then method is called as in a second order method. If I'm taking a three slopes, then method is called as in a third orders. Then if I'm taking in a four slopes, method is called as in a fourth order method. And to take in a slopes and how to solve it, okay. So then it becomes difficult. That's what we can find in so many different equations for this, and you might have gone through it. We are solving it. But in case of MATLAB, how to solve this? This is what is the most important. So in case of MATLAB, what we can do it, maybe bad issue. Okay. So my equation start with mx double dot plus cx dot plus kx, which is equal to sum. I'll put up in a force function. So I can now solve first of all this equation to be solved into x. That is a first order equation. I need to go for a first order equation. So this is a second order equation. And this equation is second order. I need to convert that into first order. So for that purpose, I will assume first of all x1 is equal to x. Then I will take an x1 dot, I will assume it as an x2, and then x2 dot, which is equal to typically what are this equation. I can now take an x2 dot as nothing but this acceleration. Okay, this what are this acceleration. Okay, this acceleration. So how can I now write x double dot? Here it is on a, I can write x double dot. I can separate out this equation. Yeah, minus c into x dot means I got an x. And this is x2 minus k into x1 divided by m. Now I got an, a two equation of first order. One is this equation. This is my first. This is my second equation. I can now solve these equations simultaneously. That we done it in ODE solver. So for that purpose, first of all, what we have to do, we have to develop a code for it. Means in MATLAB how it works, we have an ODE solvers already available. Means whatever ODE 2, 3 is there, then 4, 5 is there. Okay, these ODE solvers are already available. Okay, and these ODE solvers can solve these equations. So for that purpose, what is to be done? I need to create a function, and that function is nothing but these two equations are nothing but a function. Then I need to supply its time. Okay, how much time I'm going to solve it. That is what and I can say. And second, the third case, third point is that I need to provide an initial condition also. So if I supply all this, it will return into it, this ODE solver function, whatever this ODE solver function, gives me output in 2 points. That is a t equal to t and x1 it will. This is one plot it can give. And t is equal again x2 it will. What that x1 means, this is nothing but my x when I started at this location. This is my x. And x2 means it's on velocity. Ultimately, what it does, it takes an integration. That is what I can say it is a x dot. And it solves it. So we'll now take a demonstration of it and see it how to do that. So can you hear me? Avdut, can you hear me?
Clearly audible.
Yeah. So to solve this, first of all, set up your directory in which you want to solve it. And then, first of all, you need to create a function, which is talking about this part, okay? That function, my function part. My first equation, and this is second equation. So here, last time we seen how to create a function. We'll write here function as a name for it. Output is my derivative because I'm going to get the dx dot and dx1 dot and dx2 dot. These both will be clubbed into a single variable. That is what I can say dx. First variable will be x1 dot, second will be x2 dot. Then I'm going to give the name as a string mass damper. That's what shortly I write SMD or something. And I'm going to supply two things. One is time and another is an initial condition. What are the initial condition? At time t is equal to 0, I have to supply x1 and x2. These are two initial conditions I need to provide. This also have two values. Okay, I'll just magnify it so that you can visualize that. So this has two numbers. This dx will have two numbers. Okay. So then I can now write this function. This function determines derivatives of states, it is called. What is meant by states? States are nothing but if you have equation, it is defined in terms of states. States means if I look into this differential equation, x1 and x2 are two states of my system. That's what it is called as in states. Okay. So functions determine derivatives of the states. Okay. Then also solves spring mass damper equation with forcing condition. Forcing condition also x square. So x1 dot means dx1. So that is x of 2. That is what in a second. That is one thing. Then dx2, which is equal to, this is what in this equation. What are this equation relates to my first equation, x1 dot is equal to x2. Okay. Then second equation is that's f minus or something I need to write. F minus c into x of 2 minus k into x of 1 and then divided by capital M. So in this case, we have not defined C, K, M parameters. That's what I need to write C, K, M here. So first of all, I will assume M is equal to 1 kg mass. C, I will assume this is zero friction, zero damping, I will assume. Then I will take as a 1200 Newton per mm something. Okay. And then what are this F is a forcing function. So normally when we do a vibration analysis or something, we carry out a harmonic analysis. I have to have some equation that is F 0 into sine of, I will take consider as an omega into t. This is what an harmonic function I'm going to provide. So in this harmonic function, what I need is I need an f 0. So I'll take an this also I'll initially put on a 0. Then I will put up an omega, maybe one radian per something. Okay. So this way we create a function. After creating a function, what is to be done? You need to save that function in that particular way. Okay. It will be saved with the same name as we have given here. Okay. So that is what we will do it. After doing this, what we can do it, we can now come back to your MATLAB, another program. This is what it does. It determines only derivatives of your states. Ultimately, what you want to integrate it. So that's what we are taking in the help of that OD solvers. So then I will go for a new script file. So here I'm going to now call upon that function, OD function, and then we are going to solve it. So this program solves spring mass damper. Then I need to have, whenever I'm going to write, I have to have three steps into the program. One is input. So before input, I need to have clear all workspace. I need to clear the screen. Also, I need to close all. Close all means if some picture is ready, figure is there, that also will get closed off. So then here as an input, you can just remember one thing here. In this case, what is the input needed into this? Solve this. We need a function which we created here. This is nothing but my function. Function is already there. So another one is a T span, means how much time you want to spend. Maybe 0 second to 10 second, maybe 20 second, maybe 100 second, whatever. That is what it is called as a T span. I needed to provide two numbers, starting point and end point. That is what is called as an ease point. And then another one is initial condition. Initial condition means at time t is equal to 0, what is my displacement? At time t is equal to 0, what is my velocity? That is what x1 and x2 values I need to provide. So this is what we can define. T span I will initially define. I'm going to start with a 0 second to maybe a 5 second or something. Up to 5. 5 is nothing. Yeah, maximum time with, up to which I want to simulate it. Another one, I need to provide an initial condition. I'll write uh, here x0 as an initial condition. In this initial condition, I have to give a two values. One is x1 value. Initially, I'll put up on both the values. That was and x2 initial condition. Then, after doing this, I have to call upon logic. Logic is nothing but an ODE. In this ODE solver, we need to call a ODE function. First of all, before solving this, we'll just look at how this ODE function works. Then I'll search it, help ODE. There will be two functions typically used in this simulation. That is 2, 3, and one is 4, 5. So in ODE function, you can just look at this. So this is a non-stick solver. I will explain it. What does that stick solver means? What is non-stick solver? So that I will take in a separate lecture for it. It's too much more theoretical. In this, ODE23 is nothing but a name of function in which you are going to solve that particular SMD function. So whatever the spring mass function should be provided as an input here. Then we need to provide in a T span, and this is nothing but initial condition. Okay, so that is what the way we are going to solve it. So then it is going to give me an output as a T. Okay, this T, and then X. This X contains two vectors. One is gives an output of x1, another gives an x2. That is what it does. I'll put up an OD23. My function name is SMD. Okay. Then I need to provide an a tspan. Then I need to provide an x0. So this is my initial condition. And then I am going to solve it. Okay. Hello.
हॅलो.
हाँ बोला.
हा, तुमच्या नोकरीवरून नंबर मिळाला.
हाँ बोला बोला. मी एक
हा.
5 मिनिटानंतर माझं एक लेक्चर चालू आहे झाल्यानंतर.
हो सर.
Okay. So we got now put this all these equations, and then ultimately you want the results. Uh, I want to plot this. So this t is nothing but a time scale, which is having in a single column. X is having in a two columns. One is x1, another is an x. So I need to separate it. Last lecture I told you how to separate these columns from this. So that's what I will write here. Displacement which is equal to x of it has in a first column. But I can write all the rows and first column. Then I will have a velocity, okay, which is equal to capital X, all the rows, second column. Then I need to write in a figure number 1, which is going to plot T versus my okay, displacement. I can give an X label, then time in seconds, okay, Y label, displacement, displacement and mm, because our unit we what are the k and m and c values we provided, that is an SI unit. That's what we can say is in mm. If you given us some other units, you need to change it here. The same way I can now do it for velocity also. Got it for another figure, that is second figure, second here in displacement, I'll write in velocity here in mm per second. Okay? Because this all you need to do in a simulation, similar type of simulations, you might have done it long back, uh, numerical methods. I'll save this. I'll give the name as an assembly. Okay. And then I will start now simulation. What is the way I need to just run here? When I run it, it will start collecting the values and everything. It will execute. We'll see the error, why this error is going to give it. This error is nothing but an error using the argument. This function we not created it. Is it? And it is in on line number 13. What is the error? Error SMD is our function which we created it. Must return column vector. Is what it is going to do it? It may be returning a row vector which he can't handle it. That's what it is showing this error. So what is to be done? You need to just go to this location. This is what in a location where this SMD function you have supplied for it. So you go back to the SMD function. In this SMD function, what is to be done? I need to just do one thing, row to column and column to row. That is what in a transformation I can do it. How can I do it? I can just put up in a dash dx equal to dx dash, which will convert row vector to the column vector, and then I'm going to save it. Okay? Once I save it, once again you run it, it will solve your problem. Okay, so it will show you the output also. What is the output it is going to show me? There are two outputs. One is showing velocity, another is showing displacement. So you can just observe there is a displacement and velocity both are zero. So can you tell me the reason for it? So basically, reason for it is what are the initial conditions provided are zero. That's the reason it is going to show me on a zero output. If I change that, okay, if I change that, what will happen? It should show means ultimately I'm going to put up on a 5 mm as in displacement in initial velocity zero. So then when I simulate it, you can observe it will show you the oscillations. What kind of oscillations? These oscillations will not die at all. Reason that what are the damping we provided here it is a zero. It should not die at all. So if we provide a damping, then these will go on reducing the amplitude. But actually, you can observe here. So small amount of damping you can observe. Something is wrong in this. Why it is happening? Once again, we'll do it. We have simulated for only 5 seconds. I'll simulate for larger time so that I can see it, how much amount of the uh, uh, damping is there. Okay. So then I will now once again simulate it. You can just look. Coming more and more damping. Even though we are not provided damping into this, observe there is no damping. This is not the reason that there is no damping in the system. The reason for this decrease in amplitude is due to the truncation. What that truncation error means? Truncation error, what it does, just I will show you in this. Uh, so if I take an wrong, I think. Yeah. Okay, truncation error is that when we are going to have a first step is here, this much amount of error is there. That will be count when it is going to take it to the next. And likewise, for per steps, it's going to increase that error. That is what it is called as a truncation error. I will give you that particular information at the stage. But So this is because of a lower kind of an approximation. What we are doing, we are only taking a second order ODE solver. That's what it is going to show me this. See, if I increase this to the 4, 5, okay, means I'm going for a higher order polynomial or something. Look at these two graphs, you will come to know. So if I simulate once again, you can just see. So these will be this kind of a damping is completely. This is this is what the way whenever we are doing using a numerical method, we need to be in a much more careful. What is the reason why it is working like this? What is the reason for this damping or maybe some deviation in the simulation or kind of thing. Okay, so to do this, okay, such type of simulation. Okay, so what is to be done? You need to first of all identify what is your input is there. If your input is not proper, then obviously your output also will not be proper. We'll now provide in a small amount of damping for this. We'll provide 5 as a damping for this. Okay, and then again I will simulate. So you can that yes, it is going to show me an adapt. It's surely it is going to decrease the amplitude per cycle. If I again reduce the damping for a smaller value, maybe 1 or something, okay, and it will take too much time for simulation, too much time to get all the amplitude to become zero. This is what the way we are step by step moving towards a realistic simulation. Okay, so if you have any question, you can ask now. I'm going to give few more things I want to add it into this. Yes, Avdut? हे लक्षात आलं का सगळ्यांच्या? येस.
Yes, sir.
हां, सगळं लक्षात आलं कारण तुम्हाला हे सिम्युलेट करायचं. Okay, कारण this may not be a part of our syllabus. Okay, but what I feel is that you should know this kind of a simulation quite easy. This is going to give you a certain kind of a base for kind of things. Now you tell me what is meant by energy law. Can you tell me what is the energy law? Energy law means what? Yes, anyone? Chaitali, Avdut, anyone can answer. What is energy law?
Conservation, sir.
What is meant by conservation? How it works? In
Hmm.
case of a spring mass damper system, just take an example.
Transformation of energy only occurs.
So how it is going to happen? So when I am going to displace, what is going to happen? This mass will store the energy in terms of what one thing. When I release it, that is stored energy is going to convert into kinetic energy, and that is what it is going to happen. So why cannot we verify that particular energy conservation? And that's very simple way we can do it. So first of all, make whenever you are going to include in a damp energy conservation, there should not be any element which will dissipate the energy. That is what in a damping. That's what I will put up on the C. Then come back to this. I'm going to put up on two equations for it. So first equation, okay, is a kinetic energy. Can you tell me what is the equation for kinetic energy? Kinetic energy, which is equal to yes, Avdut, tell me.
1/2 mx square.
M,
mv square x dot square x
yes,
dot
M
square
into velocity.
x dot.
Hmm. It's a square because I'm going to use in a dot. The reason that yesterday, last lecture I told because we have to do an elemental calculation. What about potential energy? How can I calculate? 1 by 2 into K
kx
into
square.
X. Yes, I can have a displacement. Dot. So this way we got two energies. What will be the total energy? Total energy is my potential energy plus kinetic energy should remain constant. This value should be constant over the entire time span. time span. Thus, potential energy can increase or decrease. Kinetic energy also can increase or decrease. So we want to verify it. So for that purpose, I'll take on y. I will plot one more graph here. So I will take on a third graph. With respect to time, I will plot on potential energy. With respect to time, I will plot on kinetic energy. With respect to time, I will plot the total energy. So on X label, I will say it is an energy level, and maybe some unit you can write it later. And third one, I will put up a legend for it. Legend because I have in single graph, I'm going to plot in a three plots. So first is potential energy. Second is kinetic energy. And third is total energy. So that way I can provide a legend for it. And after putting this, we'll now simulate it. But before simulation, make sure that whether YAM is available for this program. No, because we have defined in this. So that's what I need to just copy down this MCK3 values into this program. I may put this in input here, MCK or something, because it is not available because this is entirely a different function. This program is in a different set of instructions. Okay. So we'll now simulate this, and it's simply you can just observe in a fourth graph, third graph. This is what in a graph it shows. But you can't see it whether it is that's what it is. You have to took in 20 seconds of time. Reduce this to within a 2 seconds or something. Okay, so that I can get into detail how per cycle energy is going to reduce or decrease. Still, I need to reduce it to the lower values, maybe a point 0.2 or something. I can get a more detailed information. Yeah. Here in this graph, you can just one thing you can observe in this graph here that is what are the this line indicates my total energy. Blue color indicates my potential energy. This is what an upload potential energy graph, and this is what an kinetic energy. So you may be remembering that in initial part, what we have done, we have given a 5 mm displacement to the spring. Okay? When you release it, means at that particular moment, we have a maximum potential energy because it is stored into your spring. So as it is going to release step by step, it goes on decreasing step by step. Okay, and the same time, what is going to happen as this mass is taking a speed? Okay, smoothly it is taking a speed. That kinetic energy goes on in. Okay, and after some time, after a particular time, at the midpoint itself, midpoint of your entire oscillations, at that moment you will have a maximum potential kinetic energy, and your potential energy will be zero because at that particular moment your spring has a zero displacement. Okay, so that is what an exchange of kinetic energy to the potential, potential to kinetic. It happens continuously whenever you are going to do a kind of vibrations. So that's what here total energy obviously it is remaining constant. It should remain constant. So that is what then a way these equations are formulated. And MATLAB is a very nice language or is a very nice mathematical tool can be used for um, mathematical simulations. That's what you can just go on doing. This is one thing we done. Okay? We'll now done only free vibrations. We have not provided any. So we'll now include that. But before that, I would like to ask. Uh, I would like to know whether you understood whatever we learned it till now. Yeah, Avdut or Chaitali, anyone can tell me?
Yes, sir.
काही डाऊट्स आहेत?
Nice.
ओके. नाही तुम्हाला काही डाऊट्स येत असतील तर जस्ट स्टॉप मी विल अगेन आय विल एक्सप्लेन ऑन. सो after doing this, what is to be done? Next task is to, instead of providing an initial displacement with a zero force or something, what I will do, I will provide a force part. I will provide a force. So here we have a force is zero. I will provide a force as a 100 Newton or. I can just tell you one thing. In this case, this is what a spring mass. I'm going to displace it. If I put up on a motor onto this, just imagine if I put up on a motor, the motor may have a certain unbalance. Due to this unbalance, that force is going to be in a kind of a sinusoidal nature. That can be simulated. How much amount of force is going to apply to this kind of things can be simulated or can be approximately treated by this equation. That is the F is equal to F zero sin of E or something. I'll put one radian. I will put a 5 radian or something. Okay. I'll provide this, and I will now have a zero damping in this case. Okay, and then I will start simulating. Meanwhile, I need not worry about this spring. What are the energy calculations? I'll just comment those energy calculations because doing a force vibration, we don't need an energy calculations. We'll do it sometime later. Okay. I'll now just simulate this and I will say it how the displacement variation, force variation it happens. Okay. This is what and for only 2 seconds, 0.2 seconds. I'll provide maybe in a 10 seconds. We'll simulate this. Ah. So you can observe something is there. What is this? This is what in a displacement profile. This is what in a velocity. Okay. So I'll now change something more. It is instead of 5, I'll grow, provide maybe a 1 or something as a frequency. Mhm. And then I'll simulate this. What it is going to show it. So this is what in a transient response. Okay. And if I provide a damping into this, we provide in a very small damping, and I'll provide an omega is equal to 5 something. You can just observe one thing here, very interesting part into this. Initially, you can see a very large amplitude. This large amplitude, and I will go for 20 or something. Mhm. Here, uh, here you can observe initial phase. Here the amplitude is larger during this particular phase, but later on your amplitude remains constant. Means what are the input force? The same amplitude you can find it here. The reason for this is nothing but a transient. What is meant by transient? Transient is due to whenever you are going to change the state of your system. State already I told there are two states of your system. One is displacement, another is velocity. Okay. So any of the state you are going to change it, obviously your system will excite some of the natural frequencies. And due to that, to damp out this natural frequency, you need a damper in it. If I provide a more damping or less damping, if I provide a lesser damping, you can find it will take too much time for simulation. It will take too much time to die out. So still it is taking time. After even 20 seconds, you can observe there is some kind of oscillations into this. Okay. Here I will provide only point 0.1 or something. You can just look at here how it happens. Yeah. At this point, it is something more kind of thing. This is going to happen. So this is what in a force and I will just do one thing into this. What is meant by square root of a by m? It's a natural. Okay. So, so if I provide uh, input force with the same frequency of my natural frequency of system, what will happen? Obviously, there will be a resonance. Okay. Two, we'll see it what is going to happen at the resonance. I'll just provide an input frequency is equal to a natural frequency. You can just observe this is what it is. continuously increasing the increasing the amplitude means sometime it will go to the infinite after few seconds of or few minutes of time it will go to the infinite and it will break because there is no this is what in a resonance condition. And if I change that frequency, maybe on a 95% of that much, I'm just going nearer to my natural, not going exactly at the natural. What will happen? You might have seen one experiment, that is what it is a resonance experiment, uh, sonometer experiment. So this is what in a bits phenomena you can have. So these are the different ways by which we can simulate the spring mass damper system. You can simulate a mechanical system. So many things we can do it using a MATLAB tool. So this is very handy tool and you can play with it. This is okay. Although if you have any question, you can ask me.